introduction, for hosting me. Well, this is based on my joint work with my former advisor, Kitagawa, and it was published in the Annals of Applied Statistics last year. And as some of you know, there's a European causal inference meeting that's going to happen later this week. And Felix will also be there. So if you want to also meet him, you can go there to the other to the lesser major university. So I'll start with the motivation for this project. So explaining group disparities is a very central task for social and health scientists. For example, we may want to explain the gender wage gap, the racial disparity in health, or the intergenerational income persistence. In other words, the disparity in income attainment by income origin. If you open like any journal in sociology, in economics, in epidemiology, in public health, you'll see a lot of this type of questions. And essentially, these are all the same question, which is how does an intermediate treatment and its effect explain the group disparity in an outcome? So now I want to first make a rather philosophical argument. So I think explanation and attribution are inherently what if or causal questions. Because for some aspect of a treatment to explain the disparity, hypothetically intervening on that aspect of the treatment should change the disparity. And in this project, we exactly developed a decomposition framework for causal explanation of group disparities. So the empirical application of our paper, which I'll also be using as the running example today, asks the question, how does college education explain the income disparity by social origin? In other words, how does college education explain the intergenerational income persistence? By the way, you guys can feel free to interrupt me anytime for questions. So in terms of variable setup, here the group variable is parental income. The treatment is college completion, and the outcome is one's own income. So let me introduce some basic notation now. So the group variable we are going to focus on today is binary. So we use A to denote the advantaged group, and B is the more disadvantaged group. So in the empirical application, it's higher versus lower parental income groups. And right now, let's also consider a binary treatment. So it's a 0-1 variable. And in the example, it's college completion. And the outcome, we use Y to denote. And the group disparity that we are going to decompose, that we are trying to understand and explain, is the group difference in the mean observed outcome. Now, what social scientists have traditionally been using to answer this type of questions is the Kitagawa, Blender, Oaxaca decomposition, or the KBO decomposition. So the KBO decomposition is based on group-specific regressions of the outcome Y on the treatment D and some covariates X. And the KBO framework decomposes the observed group disparity into 3 components. They interpret the first component as the endowment component, which they claim is the part of the disparity that is explained by differential prevalence of the treatment. And the slope component in the KBO framework is interpreted as the part of the disparity that's explained by differential effects of the treatment. And finally, they interpret the residue as the part of the disparity unexplained by either the treatment or its effect. Now, the KBO decomposition has 3 major limitations. First, it is not causally formulated. You don't see any potential outcomes in the KBO decomposition. And second, it is not non-parametrically formulated. It is inherently tied to two group-specific parametric linear regressions. So it's not even clear like what the decomposition components represent non-parametrically, because you can't really interpret the KPO decomposition separately from the parametric linear regressions. Third, the underlying group-specific linear regressions actually assume within group effect homogeneity, which, as it turns out, actually hides a third important mechanism through which the treatment can contribute to the group disparity in outcome. So in this work, we develop a new non-parametric causal decomposition with three mechanisms, where the third mechanism is exactly enabled by allowing for general within group effect heterogeneity. Now, before formally show you what our decomposition looks like, I want to give you an intuitive illustration of the decomposition. So here we are considering two groups, the advantaged group A and the disadvantaged group B. And the solid figures are those who would benefit from college education. And the hollow figures are those who wouldn't benefit from college education. And those wearing graduation caps are the individuals who factually graduate from college. So in the first scenario, everyone would benefit from college, but there are more people factually graduating from college in group A than group B. So we can describe this scenario as differential prevalence, because we have differential prevalence of college education across the groups. And in the second group, well, in the second scenario, we have an equal number of college graduates in both groups. But everyone in group A would benefit from college, while nobody in group B would benefit from college. And we can say in this scenario, we have differential effects of college across groups. And finally, in the third scenario, we have an equal number of college graduates. At the same time, we also have the exact same average treatment effect in both groups. But in group A, only those who would benefit from college actually graduate from college. And in group B, only those who wouldn't benefit from college actually graduate from college. And we can call this scenario differential selection, because we have differential selection into college based on college effects. Now, intuitively, we should expect to say some group disparity in the outcome, which can be income attainment later in life. Also intuitively, the group disparity in income would be generated via different mechanisms across these scenarios. And this is exactly the intuition that our decomposition is going to capture. Now I need to introduce a little bit more notation, but there's nothing novel here. I'm just using the standard potential outcomes notation here. So we have the baseline individual level potential outcome y0, the treated potential outcome at the individual level y1, and the difference between these two is denoted as tau, which is the individual level treatment effect. And in our one example, that's the treatment effect of college education on income. So this is what our decomposition formally looks like. So we derive our decomposition under no more than the very standard consistency assumption. So the consistency assumption is just what we use to link the observed outcome to potential outcomes. And it's assumed in virtually all causal inference work. So we decompose the group disparity into four components: the prevalence component, the effect, the selection and the baseline. Now let's look at those components one by one. The prevalence component captures the contribution of differential treatment prevalence to the total group disparity. So in our one example, it's the contribution of differential college completion rates to the income disparity. Second, the effect component is the contribution of differential average effect of the treatment to the group disparity. The baseline component is the part of the total group disparity that's unrelated to either the treatment or its effect. And the conceptually most novel contribution of our decomposition is the selection component. The selection component is defined as the group difference in the covariance between the treatment and the treatment effect. Again, remember the treatment effect tau is defined at the individual level. So it's allowed to vary generally and arbitrarily across individuals. In other words, the selection component is defined as the group difference in the selection into treatment based on treatment effect. So I found it helpful to compare specifically the selection component with the effect component. So the selection component is about within group effect heterogeneity, while the effect component is about between group average effect heterogeneity. Now let me give you a little more intuition about the selection component. Imagine a hypothetical scenario where in the advantaged group, only those who would benefit from college actually get college degrees. Then the group A covariance between treatment and treatment effect will be positive. On the other hand, imagine in the disadvantaged group, only those who wouldn't benefit from college actually get college degrees. Then in group B, the covariance will be negative or probably 0. And then in combination, in this hypothetical scenario, the selection component will positively contribute to the total disparity. Our decomposition has a very nice interventional interpretation. And this interventional interpretation exactly explicates in what sense our decomposition provides causal explanations. At the beginning of my talk, I mentioned that for some aspect of the treatment to explain the disparity, intervening on that aspect of the treatment should change the disparity. So I think a causal decomposition, like each component of a causal decomposition should have an interventional interpretation, which is indeed the case for our decomposition. So based on the stochastic intervention notation, we can find a 3-step intervention exactly corresponding to our decomposition. In the first step, we randomize the treatment within each group. Then the selection component will be the resulting change in disparity. In the second step, we further equalize the treatment across groups. Then the prevalence component will be the change in disparity resulting from this second step. And then further in the third and last step, we withhold the treatment from everyone. And in this step, the effect component will be the change in disparity. And at the end of all 3 steps, the remaining disparity will be our baseline component. Now let me summarize the conceptual contributions of our framework first. So first, we non-parametrically formalize the causal contributions of 2 classic mechanisms that have been reviewed by the KBO framework. And these two classic mechanisms of explaining group disparities are differential prevalence of the treatment and differential average effect of the treatment. And the second, we expand disparity analysis by revealing a third mechanism through which a treatment can contribute to a group disparity. And that is differential selection into treatment based on heterogeneous treatment effect. Now I want to contextualize our conceptual contributions a little more in an application. So our empirical application investigates the role played by college education in intergenerational income persistence. More broadly, this is a special case in a very long-standing sociological literature on the so-called OED triangle. So that's the triangle of socioeconomic origin, education, and socioeconomic destination. So the general question that is asked in the OED triangle literature is, does education facilitate or impede social mobility? Sociologists have, for a long time, studied the role of differential educational attainment and differential educational effects, at least at a descriptive and conceptual level. And we are the first to formalize the causal contributions of these two mechanisms to the origin-destination association. In addition, we are also the first to reveal that differential selection into education based on educational effects could also be an important part of the OED triangle. So in other words, we study not only education and its effects, but also the interplay between these two. Now, after defining our causal decomposition, we need to identify it. So first, our mean results are based on like three pretty standard assumptions. So apart from the two especially standard assumptions of consistency and overlap, we also assume conditional ignorability of the treatment. So that's the independence between the potential outcomes of Y and the treatment indicator D, conditional on a set of observed confounders X. Now, importantly, here we only assume a conditional ignorability assumption for the treatment, but we do not make such assumption for the group birth. And that is because we aim to decompose a descriptive group disparity instead of a causal effect of group membership. Alternatively, we also developed a sensitivity analysis for the decomposition, which allows us to evaluate how much of unobserved confounding would nullify our component estimates, even if the conditional ignorability assumption is not satisfied. And second, our decomposition can actually also be estimated using instrumental variables via the so-called marginal treatment effect framework. Now we can proceed to estimation. So I first want to note that our decomposition components are linear combinations of two generic functionals. That means we just need to estimate these two generic functionals in order to estimate our entire decomposition. We developed double debiased machine learning type estimators for our decomposition, and in particular for the two generic functionals. And the way we did that was we derived the efficient influence functions of the generic functionals, and we used the efficient influence functions as estimating equations to derive the so-called one-step or double debiased machine learning estimators. And for the one-step estimator based on the efficient influence functions to be double debiased machine learning estimators, of course, we use machine learning with cross-fitting to estimate the nuisance functions. And there are three main nuisance functions in our estimator. So the pi function, that's the propensity score function for the treatment. And the mu function is the outcome regression function. And there's also the conditional expectation of D given the group membership G. So that's the group specific that's the group specific prevalences of the treatment. Our estimator has multiple desirable properties. First, it is doubly robust, which means that if we can estimate either the propensity score function or the outcome regression function consistently, then we can consistently estimate the two generic functionals and consequently our decomposition. And second, under certain specific boundaries, consistency and convergence rates conditions on the nuisance function estimators that you can find in our paper, our estimator becomes asymptotically normal and also attains the semiparametric efficiency bound. So that means our estimator is as efficient as any regular estimator can get. Now I'll return to our empirical application and give you more details on it. So again, the question we want to ask in the application is what roles does college play in intergenerational income persistence? So the data we use is a nationally representative survey data in the United States called the National Longitudinal Survey of Youth, 1979. We define the group variable to be parental income, and in particular, the top 40% versus the bottom 40% in the distribution of parental income. And the treatment is college completion, and the outcome is income percentile when the respondents themselves are in their 30s and 40s. And for our causal identification, we use 20 pre-treatment covariates as confounders. So we first need to establish that there is some disparity to be decomposed. And this is just the mean income by parental income group. So as you can see, there unsurprisingly is a huge gap in terms of income attainment between rich kids and poor kids. So now let's look at our empirical estimates of the decomposition components. So first, the baseline component actually accounts for the vast majority of the total disparity, meaning that most of the income persistence across generations actually has nothing to do with college or its effect. So this is just saying that intergenerational income persistence can have a lot more reasons other than any factors related to college education. Second, the prevalence component is positive and significant, meaning that differential prevalence of college degrees does positively contribute to the intergenerational income persistence. And numerically, this indicates that if we could equalize college education, if we could equalize the prevalence of college education across income origin groups, we could actually reduce the income disparity, the total income disparity by about 7%. On the other hand, the effect component is not statistically significant. And this is because although in both groups, the average effect of college education is pretty significant, the group difference in that average effect is actually minimal. And the most novel well, the conceptually most novel contribution is our finding on a negative and significant selection component. This means that differential selection actually negatively contributes to the total disparity. And this is consistent with a long-standing notion that sociologists have developed. And that is maybe like socioeconomically advantaged people, like they just go to college regardless of how much economic returns they can get from attending college, because going to college is more of a cultural norm for them. On the other hand, for socioeconomically disadvantaged people, going to college may be more of a strategic decision based on like anticipated economic returns from attending college. Now, let me summarize our contributions so far. So in this framework, we develop a causal and non-parametric decomposition for explaining group disparities. And this framework formalizes the causal contributions of two classic mechanisms, differential prevalence and differential average effects. This framework also reveals a third novel mechanism, which is differential selection into treatment based on heterogeneous treatment effect. And in our empirical application, we found that differential selection does play an important role in intergenerational income persistence. In terms of estimation, we developed double D-biased machine learning estimators that are flexible, efficient, and robust. We've also released an R package on Quran, which has been downloaded for almost 9,000 times so far. So far, I've only been telling you about the basic unconditional version of our decomposition. But we also have a conditional decomposition. So the conditional decomposition can be used to explain the conditional contributions of the treatment and its effect beyond group differences in some additional user-specified covariates Q. For example, we can use it to study the causal contributions of college education to the income disparity beyond prior academic achievement. And this is what our conditional decomposition looks like. So apart from the consistency assumption, now we also additionally need a specific common support assumption. So the Q variables should have the same common support in both groups. And now we have the conditional version of our prevalence, effect, and the selection components. And the baseline component is exactly the same as before. And additionally, now we have a Q distribution component. So I think the most natural way to discuss our conditional decomposition is by looking at its interventional interpretation. So again, we have a three-step conditional intervention. But here in the first step, we randomize the treatment within groups, but also within each level of Q. And the resulting change in disparity will be our conditional selection component. And in the second step, on top of the first step, we further equalize the treatment across groups, but also within each level of Q. And our conditional prevalence component will be the resulting change in disparity. And from a policy perspective, this conditional intervention can be seen as more realistic, because in our empirical application, if we choose Q to be prior academic achievement, then this conditional equalization intervention would actually preserve the factual association between the treatment, which is college attendance, and the Q variables, which are prior academic achievements. So in a sense, by doing this conditional equalization intervention, we are keeping the college education system as meritocratic as it is in the factual world. And finally, in the third step, the third step is the same as the third step in the unconditional three-step intervention, which is withholding the treatment from everyone. But here, the changing disparity in the third step will be the sum of the conditional effect component and the Q distribution component. And at the end of all three steps, again, we have the baseline component, where we have the remaining disparity as the baseline component. And this is what our EIF-based estimator for the conditional decomposition looks like. Or rather, it's what the estimator looks like for the additional generic functional that we need for the conditional decomposition looks like. So here we have some more nuisance functions apart from the same outcome regression function mu and the propensity score function pi. We also have the PG function as another nuisance function. So that's the probability of being in a group given the Q variables. And there's also this nested functional omega. So because there are more nuisance functions, well, partly because of that, our estimator has a quadruple robustness property. So if any four sets of nuisance functions can be consistently estimated, the generic functional, the overall generic functional can be consistently estimated. So we are currently working on some methodological generalization to the current decomposition framework. So in the published paper, our method can only accommodate one binary group variable and one binary treatment variable. But of course, in practice, we sometimes must deal with more complicated situations. For example, the group variable might be continuous. For example, we might want to understand disparities by parental income, in which case the group variable is actually naturally continuous. And sometimes we also have different numbers and types of treatment variables. So in the generalized framework, we'll be able to accommodate both a continuous group variable as well as multiple treatment variables with arbitrary distributions. And there are some distinct challenges in making such generalizations. For example, like how do we even define disparity when the group variable is continuous? And in terms of EIF-based estimation, when it comes to multiple treatments with continuous distributions, we also need to deal with multivariate conditional densities, which are notoriously hard to estimate. All right, I look forward to questions and comments.
I have three questions.
Okay, sure.
The first one is how did you choose 40% for the split of the income disparity? I assume that it might change if you have different percentages for the parental income.
Right. Should I answer first? I don't actually have a good answer for this. I mean, like, the choices are actually pretty arbitrary here because we have to binarize the group variable, unfortunately, because of the limitation of the current framework. So we sort of just arbitrarily chose like the 40 as the cutoff.
Okay, the second one is, did you investigate the group disparities? Why there's a difference in the group disparities by college completion with regards to what faculty they were in? for example, natural science versus social science versus engineering? Because I suspect it would differ in that situation.
That is a great point. In fact, like in combination with your first question, those two exactly point to the two directions of generalization that we are working on. Because your first question points to the direction of generalizing to a continuous group variable. And your second question points to the direction of generalizing to multiple treatment variables, or perhaps one treatment variable with multiple categories. Because of course it's entirely possible that like if we study the explanatory power of different types of colleges and different types of majors even, then maybe the explanatory power of college education may increase. But you know, again, like we currently cannot do that, but with our generalized framework, we'll be able to do that.
And then the last thing is, your framework reminds me of mediation analysis.
Right.
And how you decompose, for example, the total effect into the natural direct effect and the natural indirect effect. Where is the natural direct and the natural indirect? Oh, he came, so, okay.
I do have backup. So yes, there is a very interesting connection to causal mediation analysis. But let me first clarify on the conceptual distinction though, because in causal mediation analysis, we would be decomposing the causal effect, like some kind of average causal effect of group membership, which actually doesn't make sense when it comes to group variables such as race and gender, because like how do you do causal inference on race and gender? Like how do you like reasonably conceive of hypothetical interventions on race and gender? It's just conceptually very tricky. So instead, we choose to focus on decomposing the descriptive group disparity instead. But like at a more technical level, there indeed is a connection to causal mediation analysis, and in particular, because there are like hundreds of different like decompositions in causal mediation analysis, and the closest analog that we found in the literature is like basically this three-way decomposition, which I guess is a special case of the Vanderbilt's four-way decomposition of the total effect. So if we do want to decompose the total, the average effect of group membership, the average effect of G, then this average effect of G can be decomposed into three parts. The first is the pure indirect effect. And the second is the portion attributable to interaction, and there's a residual component. So if we additionally impose a lot of like usual assumptions that are required for identifying this type of causal mediation estimates, then we can indeed establish equivalence between our prevalence component and the pure indirect effect, as well as the equivalence between our effect component and the portion attributable to interaction. And the residual will correspond to our like the sum of our selection component and the baseline component.
Thank you very much.
I also have 3 questions. Likewise. I'll ask them one by one.
You could decompose those questions.
So the first is just a question about the overlap assumption, which is, do you think in applications like this, but in social science more generally, do you think there are scenarios where the overlap assumption is violated in the sense that maybe there are people who genuinely will never go to college? And how do you think that affects these kinds of analyses?
That is a great question.
Because it seems plausible that for medical exposures, like in medicine, I think, the overlap assumption's easier to justify. But with like social exposures, it feels like maybe there are groups of people who just will never take up a given treatment, no matter what.
Right.
There's alternatively people who would never not take it up.
Yeah.
Right.
Like you said, like richer people or people of higher socioeconomic status might go to college as a social, cultural type thing always.
Right. Well, I think there are two ways to answer that. So the first is like a technical solution. So the technical solution is simply like empirically dropping those whose estimated probability scores are either 0 or 1. And if we do that, then of course implicitly we are changing our estimate to something conditional on the overlap.
Yeah.
But at a more philosophical level, I guess there's always a trade-off, because like if you condition on something that happens immediately before the assignment of the treatment, then almost by construction you have a violated overlap assumption. Like even if your treatment is entirely randomized, if you condition on the random number that you use to randomly assign the treatment, then of course you have a violated overlap assumption. But we don't actually have a problem with that, because we don't actually need to condition on the random number in order to in order for the conditional ignorability assumption to be satisfied, right? Because the random number is not a necessary confounder that we must condition on to satisfy the adjustment criteria. So I think there's always this trade-off between the overlap assumption and the conditional ignorability assumption. Sure. If we condition on more, it's more likely that we can satisfy the ignorability assumption, but it's more likely that we will violate the overlap assumption at the same time. So I guess my philosophical view is that we cannot reason about the overlap assumption alone. We must reason about it in combination with the conditional ignorability assumption. Like if you think there's a set of confounders that we must condition on, and if we condition on those confounders, and we do violate the overlap assumption, then we do have a problem. In practice, in social science, I mean, like because you can empirically assess the overlap assumption, but you cannot empirically assess the conditional ignorability assumption. So I guess there's always a space for us to make an argument about like how unnecessary it is to condition on an overly extensive set of confounders or covariates.
Yeah, you can always argue one way, but it's hard to argue the other because you can't verify it.
Right, because if you do have empirical violation of overlap, then you definitely have violated it. Yeah. But if you, and on the other hand, you can always argue that it's not necessary to use like 20 confounders for the conditional ignorability assumption to be satisfied. It's only necessary to use 10 confounders. But conditional on those 10 confounders, you don't violate the overlap assumption. Okay. That's probably, I mean, I don't think that's a great answer to your question, but that's good. What I've been thinking about recently.
The second question was, in your results, the baseline component obviously explained the most, which I guess, yeah, it makes sense. A college isn't the thing that explains the most of the disparity. It also, the confidence interval overlaps with the total disparity. Just so I understand, does this mean that even though prevalence and selection are significant, so they do, we think, let's just say we do think they have a true effect, the prevalence and selection components on the disparity, are we saying it's still possible that despite those, baseline can explain everything? Or what does the fact that the baseline component confidence interval contains the total disparity mean?
I think this is just because of the counteracting roles played by prevalence and selection.
Oh, okay. Yeah, that makes sense.
Otherwise, if the direction of every component is positive,
then it won't contain. Okay.
I think so. Yes.
Yeah. Okay, and then the final question was about continuous groups.
Mm-hmm.
I was just interested to know how you might deal with a continuous group. So would you need to make some like assumption, like a parametric assumption that maybe the prevalence and the whatever the effect varies like linearly across the group, like some sort of slope assumption, or like how have you thought about dealing with a continuous group?
So the technical answer is no. I don't think we need to make any parametric assumption. But I think you are correctly capturing an important intuition, which is because you mentioned linear slope, and that's in fact because basically I want to write something, but
there's a whiteboard there and there's a pen just down there.
Oh yeah, markers. So basically, like my idea. Well, let's use this.
Yeah.
So basically, my idea is that first at the estimand level, we need to define like what the descriptive disparity is when the group is continuous, right? So in fact, like my current thinking is we just define it as this effectively slope estimand. Of course, we don't need to interpret this as a slope because it's only a slope if we assume a linear functional form for the relationship between g and y. Yeah. But we can also just like independently define this estimand as a non-parametric estimand. That's no problem of doing that, right? So once we define what the descriptive total disparity is, we can proceed to define the components of this total disparity by again using the interventional trick, I guess, because if you look at the 3 steps of the intervention, you'll notice that they generalize with no problem to like any group variable, right? We can still randomize the treatment within each level of a continuous group variable. We can still equalize the treatment across the entire distribution of the group variable, etc. So the interventional interpretation remains very well defined, regardless of the type of the group variable. So we can still define like essentially 4 components of a decomposition based on the intervention itself.
Yeah, because you can do this process, like you said, no matter what the group is, that you can still do this same process.
Right.
Yeah,
exactly. And the beauty of this is that, like, if you look at the interventional interpretation, actually it's also agnostic to the type of the treatment variable.
Oh yeah.
So regardless of what the treatment variable is in terms of distribution, and regardless of how many treatment variables we have, the same intervention, the same 3-step intervention can carry through.